Okay, so it's time to start today's Oxford-Waseda in mathematics session. Our first speaker is Professor Süli. The title of his talk is Navier-Stokes Fokker-Planck Systems, Existence of Large Data Global Weak Solution. So please.
So let me begin by thanking Professor Shibata for organizing this wonderful conference. It's really unfortunate that we from Oxford can't be able to be in Waseda, but we have to do what we can cope with in the circumstances. I would like to thank Professor Kubo for introducing me, but I would also like to thank Ms. Marubayashi and the IT team in Waseda University for doing a really fantastic job in terms of setting up this meeting. So as you can see from the screen, the title of my talk is Navier-Stokes Fokker-Planck Systems, Existence of Large Data Global Weak Solutions. So what I would like to tell you about is a class of models that arise in the modeling of non-Newtonian fluids, which involve the coupling of the Navier-Stokes equations to the Fokker-Planck equations. So the situation that we have is the following. You have a moving fluid which moves with velocity u, which is a function of space and time. And in that fluid, which is assumed to be a viscous, incompressible Newtonian fluid, you have long polymer molecules which are floating in the fluid. So in the models of the kind that I'm considering here, these long polymer molecules are described as a collection of beads, these little balls, which are assumed to be massless. These beads are assumed to be massless, and they are connected with elastic springs. So when you consider the various forces that act on the beads, because they are in the moving fluid, there will be Stokes drag acting on the little beads. There will be an elastic force connecting the springs. So the elastic spring force can be modeled by various spring models, and we'll discuss that also. But then also because the surrounding fluid has molecules which are bombarding these beads in a random fashion, it is assumed that there is also a Brownian force which is acting on the beads. So in terms of the notation, the velocity is denoted by u of x and t, and the position vectors of the beads are denoted by r. So r sub j will denote, with respect to a chosen fixed point in space, the position vector of the jth bead, the jth ball in this configuration. So qj is the orientation vector of the jth spring. So this qj is obviously the position vector of the j plus first, bead minus rj, the position vector of the jth bead. So models of this kind go back really a long way. So if you look, for example, at the work of Hans Kramers from the 1940s, so Kramers was a famous statistical physicist. So this is the same Kramers as in WKB theory. Wrote about models of this kind in a paper that was published in 1944, but there is earlier work that he refers to by Kuhn and J.J. Hermans. So models of this kind have been widely used in the polymer chemistry literature. And so there's a huge amount of work in physical chemistry and polymer chemistry journals by Rouse, Sim, and so forth. There is a very nice book by Bird, Curtis, Armstrong, and Hessinger, which summarizes the work that has been developed in polymer chemistry in 1980 up until 1987. Now, the problem is the following. From the mathematical point of view, there has been to date no rigorous derivation of these models from Brownian dynamics. And the lack of rigorous derivation of these models that have been used has really caused a great deal of confusion in the mathematical literature. What has happened is that mathematicians took the equations that were written down by polymer chemists, and these equations were taken for granted. And when the equations were analyzed from the point of view of existence of solutions, mathematicians hit a variety of difficulties. And as you will see from this talk, many of these difficulties arose precisely because there is no rigorous derivation of the model. So this is what I would like to talk to you about. So this is what I said. So this has resulted in a great deal of confusion in the mathematical literature concerning the form of the associated Navier-Stokes Fokker-Planck system. So for example, it was not clear in the literature whether the Fokker-Planck equation should be mixed parabolic hyperbolic or whether it should be parabolic. In some papers, the Fokker-Planck equation was considered on an unbounded domain. In some mathematical papers, it was considered on a bounded domain, and so forth. So a particularly confusing case in the mathematical literature was that of the situation when Hookean springs were considered. So Hookean springs means that in this picture that I described to you, the springs that are connecting the beads are assumed to obey Hooke's law. So what that means is that you have linear springs which could in principle stretch out to infinity. But then if the fluid is considered in a bounded domain, there is sort of a conceptual contradiction. How could you have a fluid in a bounded domain and then you have polymer molecules modeled by these springs which could stretch out to infinity? And so there are papers which do this, and including several of my own papers, and the mathematical problem that one encounters because of this is somehow breakdown in weak compactness arguments because of the fact that one considers things in a situation when one shouldn't be. A related point is the following. So it is known that one of the famous models in non-Newtonian fluids, the Oldroyd B model, can be derived from these Hookean bead springs models for dilute polymers. And so then the question arises, if it's unclear whether the form of the Fokker-Planck equation is mixed hyperbolic parabolic or parabolic, whether the resulting equation for the evolution of the stress in the Oldroyd B model should be hyperbolic or should it be parabolic? So in particular, it is open at the moment whether there is existence of large data global weak solutions to the Oldroyd B model in 3 dimensions. And some of the difficulties that one encounters in this analysis are associated precisely to the fact that it's unclear what the situation, what the shape, what the form of this Fokker-Planck equation is in these bead spring models. So the summary of the talk is the following. So these are the main contributions here. So what I would like to go through is a rigorous derivation of the Hookean bead spring chain model starting from Brownian dynamics. And so I shan't be able to go through all the results. They are covered in this paper, which is 85 pages long. So there will be a lot that I will unfortunately have to miss out, but I'll try to convey the main ideas. So here are the conclusions before I get into the details. So if the flow domain for the fluid is bounded, then the configuration space domain, so the configuration, let me just explain what this configuration space domain is. So I mentioned these orientation vectors for the polymer molecules. So these orientation vectors are of the form, they are the difference of the 2 position vectors of the 2 beads that this spring is connected to. So a typical domain for these orientation vectors is omega minus omega. I know this is strange notation, but what omega minus omega denotes is the algebraic difference of the flow domain minus itself, which contains all the differences of these position vectors. And then because we have J of these springs, the configuration space domain is the Cartesian product of J copies of these domains D in which these orientation vectors lie. So what I'm saying here is if the flow domain is bounded, then I think this is really quite logical. The configuration space domain is also bounded. So this is the first observation. The second observation is the following. I mentioned when I started off is that the beads are assumed to be massless. So at some point in the analysis, we shall let the masses of these beads tend to zero. Before taking this small mass limit, the Fokker-Planck equation, which is posed on a certain domain, which contains the position vectors, the velocities of the beads, and time, is a mixed hyperbolic parabolic problem. But then, after taking the small mass limits, so after you pass to the limit with the masses of these beads, it turns out that the Fokker-Planck equation, which is posed on the domain that is written here, containing x, the position vector of the system of the center point of this coordinate system with respect to which we are considering this, the orientation vectors of the beads and t, is parabolic. So you go from a mixed parabolic hyperbolic problem to a parabolic problem when you send the masses of the beads to zero. So the consequence of this is that because the Fokker-Planck equation is now a parabolic equation, so it contains diffusion in all coordinate directions. When you derive this Oldroyd B model from the Fokker-Planck equation, this stress evolution equation in the Oldroyd B model contains a diffusion term, which is not what is written in Oldroyd's paper. If you look back at this classical 1950 paper of Oldroyd. So this is, these are the key differences. So finally, we rigorously prove in this analysis an assertion which was stated by, again, two computational polymer chemists and polymer chemist Schieber and Oettinger using formal asymptotics, which says that when you pass to this small mass limit in the masses of the beads, you end up with something called equilibration in momentum space. So in the polymer chemistry literature, this equilibration in momentum space is taken as an assumption. So what comes out from this analysis that I will show you is we are able to prove rigorously that as you pass to the limit, as the masses of the beads go to zero, we can prove rigorously this equilibration in momentum space. So this is roughly the key contribution of the lecture. So let me now go back to my picture. So here we are again. Let me try to formulate the model. So here is our polymer molecule described by the collection of these beads and elastic springs. O here is the center of a coordinate system, which you choose arbitrarily, and Rj is the position vector of the jth bead. Qj is this orientation vector or configuration vector of the jth spring, and we have j plus 1 of these springs. This is in a moving fluid which moves with velocity u, x, and t, and the fluid is assumed to be incompressible Newtonian and isothermal. So what you see here is really just a notation. You have a long vector R, which collects the position vectors of all these beads, j plus 1 of them. Each of these position vectors lies in the flow domain, omega, and there's j plus 1 of them. Each of these has its own velocity. So you have a very long velocity vector. V1 is the velocity of the first bead. V2 is the velocity of the second bead, and so forth. And there are j plus 1 of these velocities. And then you look at the Qs. The Qs are differences of Rj plus 1 and Rj, that's Qj. And there are j of these orientation vectors, and that is Q. So QJs, as I mentioned before, are contained in a domain D. So this D is defined as omega minus omega, which by definition is the difference of R minus R hat, where R and R hat are both in omega. So because this R coordinate system is some kind of internal coordinate system which doesn't know anything about the coordinate system for the fluid, you have to connect this internal coordinate system to the fluid coordinate system, the X, Y, Z coordinate system, if you like. So X here, the X that appears in the equations that I will write down is taken to be the arithmetic average of these position vectors. So now we have to describe what is going on because we are in a moving fluid. You could take the equation to be the Navier-Stokes equation, but just to make sure that I can cover what I want to cover within these 50 minutes that I have, instead of looking at the Navier-Stokes equations, just to cut the story short, I decided to look at the Oseen system where the velocity field here in the convective term has been fixed. I'll take it to be an L infinity function which is given and divergence free. There are certain assumptions on the domain that you see here. In the physical dimension of the domain is 2 or 3. So you have the Oseen equation, but what is interesting about this equation that in addition to the usual things that you see in the Navier-Stokes or Oseen equation, you have an additional term on the right-hand side here. So what is this divergence of K? Well, K is what is called the polymeric extra stress tensor, which is responsible for modeling the presence of these polymer molecules which are in the moving fluid. So I'll define this tensor K. So you take the divergence of this tensor K, you get a vector. So this vector is what appears on the right-hand side of this Navier-Stokes or Oseen equation. We have a divergence free velocity field. You can take any boundary condition. I took U to be 0 on the boundary of the flow domain, and you have an initial condition. So what is this tensor K? So there is an expression for this in the polymer chemistry literature. It's called the Kramers-Kirkwood stress tensor or polymeric extra stress tensor, which is given by this formula here. So we'll get into the details of this formula in a second, but here is what it is. By definition, it's the sum as J goes from 1 to capital J, which is the number of these vectors, spring vectors. And what you have in this sum is the conditional expectation of lambda times Qj, which is the spring force corresponding to a Hookean spring. So Qj is the elongation of the jth spring, and lambda is a spring constant. Tensor with Qj, so this gives you a matrix or a tensor, and you have to take the conditional expectation with respect to this x variable that appeared on the previous slide. So let me just remind you, so this x here is the arithmetic average of the position vectors of the beads. So E sub x denotes the conditional expectation, and rho is a probability density function to be defined below, and this rho will be the solution of a Fokker-Planck equation. So the reason, if you are wondering why we have this expectation and random variables, so please remember that we are assuming that there is a Brownian noise acting, or Brownian force acting on the beads. So there is a bombardment of these beads that describe the chain by the molecules of the surrounding fluid, and it's assumed in the model that this is Brownian. So this rho is going to be a probability density function to be defined below as a solution of a Fokker-Planck equation. So before I write down the Fokker-Planck equation, just one piece of notation. So U is the velocity field from the Navier-Stokes or this Oseen equation. And there is this notation script U, which is the collection of velocities evaluated at precisely the locations where these beads are placed. So U at R1 at time t is the velocity at position R1 time t. But because we have this K on the right-hand side of the Fokker-Planck equation, U itself also depends on the probability density function rho, because the probability density function is involved in the definition of this tensor K. So this is this notation script U. So let me now try to describe the equation of motion for the beads. So remember, this R was a huge vector which collected the position vectors of the beads, and the equation of motion for that vector is basically Newton's second law. So mass times acceleration is equal to the various forces that act on the beads. Epsilon square is the mass of a typical bead, and in the end we'll let this epsilon go to 0, but for the moment epsilon square, which is the mass of any of the beads, is fixed. So mass times acceleration, and then you have to think what sort of forces act on the beads. So there is Brownian noise, there is Stokes drag, so you see the velocity here of the bead, but because these beads are in a moving fluid, what you have to do here is subtract the velocity from the velocity of the bead. You have to subtract off the velocity of the fluid, and you have Stokes drag. So that's another force that is acting on the beads. And finally here, you have to describe these springs that connect the beads. And in this discussion, I'm going to assume that we have linear springs, so Hookean springs. So you have this matrix capital L here, which describes somehow the configuration of the topology of the spring. We are dealing with a linear spring. So each of the beads is connected to two other beads. So this is why we have this tri-diagonal matrix, except for the first and the last bead, which only have one neighbor on one side or on the other side. So there's a drag coefficient here also, and that drag coefficient plays absolutely no role in the analysis. I'm going to set it equal to 1. So we have a second order stochastic differential equation, but the second order stochastic differential equation can be rewritten as a system of two first order stochastic differential equations, except that in the first equation, there is no noise. This Brownian noise only appears in the second equation. So if you use the substitution E times R dot is V, then this equation, the second equation, contains noise, and it's EV dot equal to this right-hand side. So in some sense, this system of stochastic differential equations is degenerate because there is no noise in the first equation, but there is noise, Brownian noise, in the second equation. So nevertheless, this pair of vectors RV is a random variable. So you can think of the probability density function, which is associated with this random variable. And you can write down the evolution equation for this probability density function, and this will be our Fokker-Planck equation. But then, because the law of RV depends on the probability density function itself, because the Fokker-Planck equation will contain this velocity u here, and this u depends on the probability density function, which is the probability density function of R and V. What we have here is what is called a McKean-Vlasov diffusion, in fact. So let me now get to the definition of this polymeric extra stress tensor. So the expectation of this expression here, which is the spring force tensored with Qj, so lambda Qj tensor Qj is, so this is the standard definition of expectation, is given by this formula where rho is the probability density function. So at this point, what happens is we perform a change of variables, and working instead of working with the position vectors of these j+1 beads, we perform a linear change of variables, and we switch from these r coordinates, which are the position vectors of the beads, into a new coordinate system, which consists of the position vectors of the orientation vectors and this x vector, which is the arithmetic average of the position vectors of the beads. So what we have is basically a change of variables, and this is a linear bijection. You can work out the Jacobian, and it turns out that the Jacobian of this transformation is 1. So if you perform this change of variables in this expression, what you end up with is that this expectation is equal to basically the same thing as above, but now instead of R here, you write B Qx, where B is this affine mapping that takes you from the original R coordinate system into this Qx coordinate system. And then finally, this polymeric extra stress tensor that appears on the right-hand side of the Oseen equation, this K tensor, is the conditional expectation of this expression. So we have the expectation above, and we have to condition this on the fact that the arithmetic average of the position vectors is precisely this position x. And this conditional expectation is what is written here. So once again, so you have the flow equation. On the right-hand side of the flow equation, you have the divergence of this K tensor given by this formula, which involves this function rho. The function rho, on the other hand, is a solution of a Fokker-Planck equation, which I'm going to state. So here's the Fokker-Planck equation, and the derivation of the Fokker-Planck equation follows the standard procedure based on Iter's formula. So you end up with this partial differential equation. And what is interesting about this partial differential equation is the following. So if you look at this term, what you see is a drift term, a transport term in the Vj direction, and there's also a diffusion term in the Vj directions. If you look at the other derivatives here, you see drift terms and you see no diffusion with respect to the other variables. So this is caused by the fact that the stochastic system of stochastic differential equations is degenerate. There was no noise in one of the equations and there was noise in the other equations. So you get diffusion with respect to these Vj's and there's no diffusion. So at this level, the Fokker-Planck equation is parabolic in the V directions, but it's a purely transport equation in the R directions. So what we will see later on is that when we pass to the small mass limit, when we send epsilon to 0, the resulting equation will no longer have this mixed hyperbolic parabolic structure. It will be a purely parabolic equation. That's going to be important. So I don't want to get into details here. You can also tag on certain boundary conditions to this equation because we are in a bounded domain. So in the analysis, we considered what is called the specular boundary condition, which simply means that if one of the beads hits the wall of the flow domain, it is reflected with the same velocity as the one with which it hit the boundary of the domain. But it's not particularly important for the analysis that will follow. Okay, so let me now move on to the analysis. So let's look at the existence of solutions to this model. So I need some notation. First of all, let us define what is called the Maxwellian. So V is the velocity vector of the beads. There are j plus 1 of these beads. So this V is a massive vector in j plus 1, that's the number of beads, times d. D is the physical dimension components. So this Maxwellian is defined by this formula. So it's sort of a normalized Gaussian function. And then we rescale the probability density function. We solve this Fokker-Planck equation with the Maxwellian M. We have an initial condition that is prescribed to us, rho 0, and that too is rescaled by this Maxwellian. So these hats simply denote functions which have been rescaled by the Maxwellian here. So what will be important in the analysis is the following function, s log s minus 1 plus 1, this f of s function, which has this shape. So it's a strictly convex function with superlinear growth at infinity. At 0, it's equal to 1, and at 1, it is equal to 0. And we consider this for non-negative s's. The reason why this function is important is because we want to impose certain conditions, certain assumptions on the initial condition. The probability density function by nature is an L1 function. So this is this rho 0 here. It has to be non-negative. Its integral has to be equal to 1, and here's the function f. So what we are assuming here is that the Maxwellian times f of rho hat 0, and where rho hat 0 is rho 0 divided by m, is in L1. So what this means is, in physical terms, is that the initial condition has a finite relative entropy because this s log s function is associated with entropy. So these are the assumptions on the initial condition. So let me get into the existence of solutions to this problem. So how do you prove existence of solutions to this problem? So at the moment, the Fokker-Planck equation is parabolic in certain directions and hyperbolic in certain directions. What we're going to do is fix the velocity field for the moment. We'll assume that it's sufficiently smooth and study the Fokker-Planck equation. So this is sort of the first step in the analysis. And then in order to be able to show existence of solutions to the Fokker-Planck equation, we perform a parabolic regularization of the Fokker-Planck equation by adding diffusion terms in the directions where these diffusion terms are missing. And these are the R directions. In the V direction, there is diffusion. So we also strengthen temporarily the assumption on the initial condition. So instead of what I wrote down as an assumption on the initial condition on the previous slide, temporarily we'll assume that this rho hat 0, this initial condition normalized by the Maxwellian, is in L2. So it's in this Maxwellian, so the subscript M denotes a Maxwellian weight. So it's in a Maxwellian weighted L2 space, and it's non-negative. So then we use standard parabolic theory, assuming that the velocity field has suitable regularity. Sobolev regularity. We show the existence of weak solutions to this regularized, alpha regularized Fokker-Planck equation, where I added in diffusion in the directions where it was missing. So the star notation, so let that not confuse you. So this simply means that, so star stands for the imposition of the specular boundary conditions that I mentioned before. But again, this is not particularly important for the purpose of this talk. So in any case, we proved the existence of solutions to this Fokker-Planck equation after the alpha regularization. So one can also show that rho alpha, so if you go back from these hatted variables to the original probability density function by multiplying through by the function m, which you used to divide by previously, you get this function rho alpha, which is a probability density function, integrates to 1, and using standard cutoff method, it is possible to show that it is non-negative. So then we pass to the limit with this alpha regularization because we want to take out this artificially added in diffusion term from the Fokker-Planck equation. So we pass to the limit with this alpha coefficient that has been added in with that diffusion term, and you have various weak convergence results which allow you to pass to the limit in this regularized equation. So the limit ends up to be a non-negative function. It integrates to 1, so it genuinely is a probability density function. What is also interesting is that you get an energy estimate for the solution of this Fokker-Planck equation. This really is going to be very important. So where does this come from? So the process for deriving this energy estimate is as follows. So you take the Fokker-Planck equation, whose solution is this normalized probability density function rho hat, and you test the Fokker-Planck equation with the logarithm of rho hat. You perform certain integration by parts, and you end up with this energy estimate for the solution of the Fokker-Planck equation. So this is sort of a really important ingredient in the analysis. As you can see, there's certain assumption on the velocity field for us to be able to do this. And what appears here is f of rho 0, and this is precisely the assumption that was made on the initial condition that this integral here is finite. So this is step 6 of the argument. So there's a small remark here. We supposed that a rho hat is in L2, in this Maxwellian L2 space, for technical reasons temporarily, but as you can see from this bound really only depends on sort of a weaker quantity on the Maxwellian weighted L1 norm of this f of rho hat. There are also various constants here, and what will be also important is, because this is precisely the inequality that we'll use to pass to the limit, is that the right-hand side here is completely independent of epsilon, the masses of the beads. So now we couple this to the Oseen equation. So having proved the existence of solutions to the Fokker-Planck equation for a fixed velocity, now we look at the Oseen system, and what we'll do is perform an iterative process, and then we'll pass to the limit in this iteration. So we consider an iteration where it is assumed that the velocity field is given, and you consider the Fokker-Planck equation. And then for the solution of the Fokker-Planck equation, whose existence we have shown, we go back to the Oseen equation and we'll iterate. So in terms of the initialization of this Fokker-Planck equation, what appears here is rho 0 hat k. So this function here was supposed to be in this Maxwellian weighted L2 space, but that is not the assumption that was originally made on the initial condition. So we'll have to worry about this. We'll have to deal with this issue. So in order to deal with this issue, we do the following. So originally this rho 0 hat was a function which was assumed to have finite relative entropy. So what we go through here is a renormalization of that initial condition. From that original initial condition, we create a sequence of initial conditions through this renormalization function, which lie in this Maxwellian weighted L2 space in order to be able to show convergence of this iterative process that I described to you on the previous slide. So this renormalization has some nice properties, and it guarantees that rho 0 k is in suitable spaces, and you can deduce various convergence results for this renormalization. So this is going to be important. So then from this previous energy inequality that I stated, this energy inequality applies to the solution of the Fokker-Planck equation. This is precisely what was written before. The only thing that has changed compared to that earlier energy inequality, I have inserted this index k, which denotes the iteration number in this iteration between the Oseen equation and the Fokker-Planck equation. So here we are, and it will be shown later on that this sequence UK that arises from this iteration in this between the Fokker-Planck equation and the Oseen equation is in fact a bounded sequence, uniformly bounded with respect to k in L2 norm in time and L infinity in space. So this C, as you will see when we get to step 13, is a constant independent of k. So having guaranteed the solvability of the Fokker-Planck equation, now we look at the Oseen system. So for a given probability density function rho sub k, we consider this polymeric extra stress tensor k, which depends on the probability density function. We stick it into the right-hand side of the Oseen equation, and then one can solve the Oseen equation and generate a new velocity with which you go back to the Fokker-Planck equation, and this is this iteration process that I described to you. So this really is a standard problem. It's a linear sort of fluid flow problem. There's nothing particularly exciting about it. It's straightforward to show the existence of a unique solution to this Oseen equation for this given right-hand side k sub k. One can check that this sequence of polymeric extra stress tensors is in fact uniformly bounded. So as you send k to infinity, this sequence remains bounded. So this is really quite important, because what follows from this is that the sequence of polymeric extra stress tensors, weak star converges to something that has to be identified in L infinity. So weak star converges in L infinity in space-time. So then the next question is, what exactly is this object K that these polymeric extra stress tensors have converged to? You would like to show that the limit is what you expect it to be, namely it is this tensor, which is similar to K sub K, except the index K is erased. But showing this is not straightforward, so we'll return to this in subsequent steps. So then it turns out that because of a standard embedding, so this is the set in which the initial condition for this Oseen problem has been chosen. It's embedded in L2. You can deduce uniform bounds on the sequence of solutions to the Oseen problem. So then by function space interpolation, this sequence UK plus 1 is also bounded in L2 plus 4 over D in space-time. And this helps you to deduce that also B, which has been assumed to be L infinity, and this is the coefficient in the Oseen equation, tensored with UK plus 1, is also bounded in the same norm, and therefore K sub K, which is in L infinity, minus B, tensored with U sub K, is also bounded in this norm. So the reason this is important is we'll look at this Oseen equation and move all the terms, which are not the Stokes terms, but all the terms on the right-hand side, and we have control on the right-hand side of that Oseen equation. So then we appeal to maximal regularity theory for the Stokes problem, and so this is a result by Koch and Solonikov, which implies that the sequence of solutions to the Oseen equation in this norm is uniformly bounded, and it's uniformly bounded because everything on the right-hand side, according to the previous step, is uniformly bounded. And this is what is written here. So now the solution of the Oseen equation is bounded in this norm. So then by Sobolev embedding, this sequence of velocities is also bounded in L2, L infinity, because this space, Sobolev space, is embedded in L infinity. So this then allows us to pass the limit weakly in L2 for the velocity and weakly for the derivatives, time derivatives, and strongly by Aubin-Lyon's lemma in this norm. So then this allows us to pass to the limit in the Oseen equation. And as I said before, what is this k? Well, this k, when you pass the limit, still remains to be identified. So we must identify this weak star limit k of this sequence k sub k in terms of the probability density function. So the way this is done is we look at the Fokker-Planck equation and we move pretty much everything that is ugly across to the right-hand side of the Fokker-Planck equation. And the remaining terms on the left-hand side that survive here define a hyperelliptic operator. So you have a hyperelliptic operator with some terrible stuff on the right-hand side. But it turns out that this terrible stuff on the right-hand side can be controlled. And the initial data can be also controlled. So you can show various properties for the initial data of this Fokker-Planck equation. You can show boundedness of the sequence of initial data. You can show equiboundedness of the sequence of initial data. You can show boundedness of the sequence of these right-hand sides that have been moved over to the right-hand side of the Fokker-Planck equation, and equiboundedness of the sequence of right-hand side. And then by appealing to an argument which is due to Di-Perna and Lyon's, one can deduce, thanks to hyperellipticity of this differential operator, you can deduce strong convergence of the sequence of probability density functions in L1. So this is really quite important in terms of identification of this limiting extra stress tensor. So there is a technical argument, I can't go into the details, but eventually it turns out that you can identify the limit of this weak star converging sequence as what you hope it to be, namely this fraction here. So basically at this stage, you have shown the existence of weak solutions to this coupled Oseen Fokker-Planck system for a fixed bead mass epsilon. So what comes next is a passage to the limit as epsilon tends to 0. Remember, epsilon was the mass of each of these beads. And now we would like to see what happens to this system as we let the masses of the beads converge to 0. So let's look at the small mass limit and this question of equilibration in momentum space. So what we have shown by this point is that for a fixed epsilon, for a fixed bead mass, we have a solution to this Oseen equation, which is in a nice space. And the probability density function for that fixed epsilon also has certain regularity properties, which are written down here. And this probability density function, this is what we have shown, satisfies in weak form a certain Fokker-Planck equation, which is written down here with certain test functions. And now we would like to pass to the limit as epsilon goes to 0. And what is written here is simply the initialization. So here is this energy inequality that I keep coming back to. So it follows from what we were doing before is that the probability density function for a fixed epsilon, for a fixed bead mass, satisfies this energy inequality. And what we would like to do now is use this energy inequality to pass to the limit with epsilon. We want to send epsilon to 0. So you see from this energy inequality that you get various bounds on what appears in the energy inequality. So for example, this object here is because the right-hand side is independent of epsilon, is bounded in L infinity and this Maxwellian weighted L1 norm. This other guy here that appears in this term is also bounded in L2 and so forth. So this allows you now to send epsilon to 0. You have a weak convergence in LP of the probability density function to something that I will denote by rho hat subscript 0 in brackets. So please don't confuse rho 0, which was the initial condition, with rho hat 0 in brackets. So the 0 in brackets is the limit as epsilon goes to 0 of the probability density function. And similarly for the other quantities. So also because we had this uniform bound from before, we have a uniform bound on the sequence of u epsilons, and they converge in a certain sense to a limiting function u subscript 0 with a bracket. So finally, this is the second term in our energy inequality. If you move the prefactor epsilon, so let me just jump back to the previous slide. So this is the term that I'm talking about. So this is a non-negative term, you can drop it, and what you have is a bound on this term in terms of this quantity, which is independent of epsilon. You move the epsilon square to the other side and you send epsilon to 0. And what you find is this inequality for that second term, and what this implies is that these derivatives in here must be equal to 0. So what that means, if these derivatives are equal to 0, what that means is that the function that is underneath here is independent of Vj, because the derivative with respect to Vj is equal to 0. So these limiting functions, as you send epsilon to 0, are of the form some function of r and t, but not of v. There's no more any v dependence because these guys here are equal to 0. These derivatives with respect to Vj are equal to 0. So what we have shown, in fact, is that in the limit as epsilon goes to 0, the limiting function is only a function of r and t, but because these Hettich functions were the ratio of the probability density function and the Maxwellian, what you have is that the original probability density function, which is the Maxwellian times rho hat, is of the form Maxwellian times what rho hat is, and rho hat is of the form rho of t, so some function of rho of t. This limiting function as epsilon goes to 0 has this factorized form, so it's a product of the Maxwellian, and this function eta, which is only a function of r, not of v. And this is what in the polymer chemistry literature is called equilibration in momentum space, this factorized form, as you pass to the small mass limit. And so what we have here is a rigorous proof of this equilibration in momentum space. So then the small mass limit of the coupled Oseen Fokker-Planck system finally satisfies this Oseen equation with divergence of the limiting tensor K0 as epsilon goes to 0. So once again, this K0 has to be identified as epsilon goes to 0. So again, this is a technical argument involving compensated compactness based on the Diffie lemma to identify the limit as epsilon goes to 0. And finally, this function eta, to which the probability density functions have converged to, and so this is what appeared on the previous slide, satisfies this Fokker-Planck equation. What you see in this Fokker-Planck equation, that ultimately this function satisfies a parabolic equation, not a mixed hyperbolic parabolic equation, but a parabolic equation after you have passed to the limit, because there is diffusion in all of the coordinate directions. So I'm coming now to the end of the talk. There's just this slide and one more slide. So the only thing that has to be done, remember in the beginning when we started the discussion, there was this change of variables. We switched from the original coordinate system to this coordinate system that we have carried out the analysis. So now we switch back to the original coordinate system. And what we end up with is this Fokker-Planck equation with respect to t time x, so this is the location in the flow domain, and qj are these orientation vectors in the configuration space. And because this equation comes from this parabolic equation on the previous slide through a linear change of variables, and the original equation here was a parabolic equation after this linear change of variables, sure enough, the Fokker-Planck equation is a parabolic equation, and I emphasize the presence of this diffusion term in the parabolic equation. So it's fully parabolic, not mixed parabolic hyperbolic. And so this fractal m that appears here is once again a Maxwellian, but this is now Maxwellian with respect to the q variable. So this is my last slide, just a small remark. frequently it is assumed that you have a homogeneous fluid in the sense that the initial probability density function is such that its integral is independent of the x variable. So somehow spatially homogeneous probability density function. And if you denote this integral here, which is now a constant because you've integrated with respect to q and you have assumed that it's independent of x, you denote this constant by any letter. Let's say 1 over n is the letter. What you end up with is that the integral of the probability density function is constant in time also. So it too can be shown to be equal to precisely this number n to the -1. And in that case, there is a simplification of the probability density function, this limiting object that you have converged to. Remember, originally this was a fraction because it was a conditional expectation, because now you have this homogeneity assumption. The denominator in that fraction is a constant. You can rewrite that expression like so, with n here being coming from this n to the -1. And this expression is precisely what Kramer's expression is for the polymeric extra stress tensor, and this number n is called the polymer number density per unit volume. So basically, to summarize, we have a rigorous derivation of this model, and the key observation is that the Fokker-Planck equation that you end up with after you have passed to the small mass limit is a parabolic equation with diffusion in all coordinate directions. And therefore, if you derive from this Fokker-Planck equation, the stress evolution equation in Oldroyd B, that stress evolution equation in Oldroyd B coming from this model will also be a parabolic equation and not a hyperbolic equation. So finally, there are some references here, but I'll leave the slide here, and I thank you very much for your attention.
Thank you very much for interesting talk. Are there any question, comment? Professor Giga? Professor Giga, please. Okay.
Yes, I have a short question. My question is very simple. You use deep Carl lemma, yes?
Yes.
And what structure allows you to use deep Carl?
So this is
maybe
interesting. So yes, thank you very much for the question. So it's not easy to explain, but it is a deep Kerr lemma in space-time. So I'm desperately looking for a form of the Fokker-Planck equation where I can point out this in sort of an easy way. So what happens here? So can you see the slide? Can you see my mouse?
Yeah.
So the Maxwellian here is independent of time. So you can take this Maxwellian, you can put it under the time derivative.
Okay.
So then this is a constant, you can move that in underneath here and so forth. So what happens here is on the left-hand side here, you have something that has a divergence form in space-time.
Space-time divergence, I see.
So it's a space-time. So the Diffie-Kerr lemma is not in space, but it's a space-time Diffie-Kerr lemma.
I see.
Professor Süli?
Yes.
Can I hear?
I can't. Okay. I can hear you, but I can't hear the question.
Yeah. So you explained the left-hand side is a space-time divergence, right?
Yes.
And yes, and you say more things, but the machine does not allow me to listen. So.
So shall I repeat what I said?
Yeah. Thank you.
Yes. Okay. So there are lots of technicalities, but basically the key point is that so maybe I'm sorry, maybe I'm pointing at the wrong slide. So let me just find if it's written down. So I think this is a good place to look at. So what happens here is you have a time derivative on eta, you have a space derivative on these guys, and you have a space derivative here. So you have an operator which is in divergence form in space-time. So you can think of a vector. The first component of the vector is eta. The second component, well, it's going to be a long component because there are j plus one of these. So you form a very, very long vector. And so the first component is eta. The second component are the components of j plus one components of this vector. And then the third component is what is here. But this is an expression in divergence form. So this is somehow the idea.
Okay, thank you.
Okay, thank you.
Thank you very much.
So- Okay, sorry. We have no time, so I'll stop here. So thank you very much for thank you very much, speaker again.
Thank you very much indeed. Thank you very much for having me.